Close the door. And yeah, when you begin to speak, wait a little bit so I can cut the video.
Good afternoon, everyone. Welcome to Conference Seminar on Wednesday. Today's speaker will be Haozhe, or in Chinese, Haozhe. He obtained his Bachelor of Science in Atmospheric Science in Nanjing University of Information Science and Technology, and afterwards he obtained his Master. That was my bad. Can I restart?
Yeah, I think you also said today's video will be, if I heard that correctly, should say today's speaker will be.
I'm so sorry.
Yes, okay.
Okay.
That's how it is in TV productions.
Good afternoon, everyone. Welcome to Wednesday's conference seminar. Today's speaker will
I think we will leave this in the video.
too much coffee. All right, chill. Good afternoon, everyone. Today's topic. Sorry, again. Just kidding. Good afternoon, everyone. Welcome to the. Can you do this? I can't do it.
Do it without the paper. Just stand in front of the screen and talk.
Okay.
Don't read. Just talk.
I don't know. I just can't stop laughing.
Don't look. Just talk.
Good afternoon, everyone. Welcome to Wednesday's conference seminar.
Just keep going.
I don't know why this is so funny. Okay.
Now you are half in the light and half in the I think it was good to stand in front of the whiteboard there.
Okay. I'm so sorry. Good afternoon, everyone. Welcome to Wednesday's conference seminar. Today, our speaker will be Haozhe, or in Chinese, He Haozhe. He obtained his Bachelor of Science in Atmospheric Science in Nanjing University.
Just continue.
Okay. He obtained his Bachelor of Science in Nanjing University of Information Science and Technology, and his Master of Science in Global Climate Change from Beijing Normal University. Later on, he joined a Rosenstiel school under the supervision of Dr. Brian Soden to pursue the PhD degree in atmospheric science. His current research interest is in radioactive forcing, feedback, and climate sensitivity. Thank you so much for coming, Dr. He, and please give your talk.
Thank you, Jason. Hi, everyone. Thank you for attending my 1-hour seminar. I'm totally flattered. In this talk, we will explore some questions in climate change field and try to better understand future warming. So this talk will cover 4 works we have already done if I have enough time, and some potential idea for the future works. So the overarching objective of this work is to quantify and understand the cause of intermodal spread in radiative forcing and feedbacks in climate models and their implications for climate sensitivity. So what's the equilibrium climate sensitivity? The so-called equilibrium climate sensitivity is a change in the global mean surface air temperature required to restore radiative equilibrium in response to a doubling of CO2 concentration. The climate sensitivity is the most widely used metric to quantify the susceptibility of the climate to an externally forced change. However, it's difficult to obtain equilibrium climate sensitivity since it requires thousands of years simulation. Here, the alternative effective climate sensitivity is the one mostly used based on the shorter simulation, since it's reasonably correlated with other sensitivity measures and warming by the end of the century, indicating the ECS is a useful measure. A recent work showed the single most important metric increase in CMIP6 with lots of models with the climate sensitivity greater than the estimate range by HCC ARC's report, highlighting the need for better understanding the cause of the intermodal square in radiative forcing and feedback in climate model and their implication for climate sensitivity. Here I will start from a feedback work. The work uses observed interannual variability to constrain climate feedback and further narrow climate sensitivity uncertainty. This work will focus on the cloud and lapse-rate water vapor feedbacks. Why we care about them? Here I show the global mean feedbacks for CMIP3, CMIP5, CMIP6 archive. For cloud feedback, it's persistently the largest uncertainty. Uncertain source of the net feedback and further the source of the climate sensitivity uncertainty. ET squared is dominated by the local related short-wave cloud feedback uncertainty. Another one with considerable importance in understanding climate sensitivity uncertainty is the lapse-rate water vapor feedback. Even though there is a cancellation between the lapse-rate water vapor feedback on both magnitude and uncertainty. Then I will give a brief introduction of the emerging constraint theory. The key idea is models failing to reproduce observed statistics should not be charged for future climate projection. Here I would use the figure from the Klein and Hall as an example to clarify how it works. The scatter plot here shows the albedo sensitivity from the seasonal cycle of the control run versus that from the climate change experiment. Blue dots from the from models of CMIP3, while the red dots show the models from CMIP5. The vertical solid line and shading are the estimation from observation. In this case, if we only consider model with sensitivity consistent with observation, we can have a narrow range for the CMIP3, also for the CMIP5. Here, need to note we will use observed interannual feedback as an emerging constraint for this work. The premise of this work is the consistency of climate model climate feedback between interannual variability and long-term warming supports the use of interannual observation in assessing climate feedbacks. Then we will move on to our own results. For global mean cloud feedback, we show a scatter plot that is interannual feedback from the PI control run by regression deseasonalized cloud radiative response against surface air temperature versus the long-term cloud feedback by regression annual mean cloud radiative response against the surface air temperature. Here we can see a strong correlation and a comparable intermodal square between them if we only consider models for within observed confidence interval. The intermodal square of the long-term cloud feedback could be narrowed by 1/3. However, the emerging constraint method doesn't work for the lapse-rate water vapor feedback, since the interannual feedback, since the interannual square is much larger than the long-term square, and the observation has a range comparable to the intermodal interannual square. Virtually, no model can be excluded. The worst thing is if we use different temperature and humidity profile, we will see a larger large difference among these different observations, so it's indeed difficult to constrain the long-term lapse-rate water vapor feedback. If we check the lapse-rate water vapor feedback value separately, we would find even larger difference among these observations. In terms lapse-rate feedback, else results show different size compared to the two reanalyses. And for the water vapor feedback value of else are generally smaller than those of reanalysis. So this is due to else loose sensitivity to humidity and accuracy of temperature at the upper troposphere. So it will be interesting to combine to check the feedback result using a combination of else and also MIRS from the higher altitude. If we look at the local cloud feedback contribution to the interannual and long-term global mean cloud feedback spread, which are shown here, we can compute them using regression of local cloud feedback against the global mean cloud feedback across all models. We find similar contribution patterns are shown on both interannual and long-term time scale. This suggests similar physics behind them. More specifically, consistent behavior of the low cloud change on both interannual and long-term time scale. These are evidence that validating the effectiveness of observed constraint on cloud feedback. Similarly, we apply the regression method to the lapse-rate water vapor feedback. Some interesting points are shown. First, the global mean lapse-rate feedback is dominated by tropics. Second, distinct local contribution patterns are shown. Hemispheric symmetry for the interannual one and asymmetry for the long-term feedback. This highlights the challenge trying to use observation to constrain long-term lapse-rate water vapor feedback, since intermodal spread of long-term lapse-rate water vapor feedback is driven by a contribution pattern which is not observed on interannual time scales. We further found the largest contribution over tropics come from the uncertainty in relative humidity feedback, and all the uncertainty of tropic relative humidity feedback dominates the spread of global mean lapse-rate water vapor feedback. As you can see from the scatter plot between long-term lapse-rate water vapor feedback and relative humidity feedback. Brief summarize this part. So observed interannual variation provides a useful constraint to narrow the uncertainty in long-term cloud feedback. It's impossible to constrain the long-term lapse-rate water vapor feedback uncertainty with wearable observation and the spread of global mean long-term lapse-rate water vapor feedback is dominated by tropics, where the largest contribution from the local uncertainty in the relative humidity feedback. Then we will move on to radiative forcing. I will show an easy and effective way to diagnose the equilibrium climate sensitivity first. So the ECS is supposed to be calculated as a quotient of radiative forcing and feedback. Most of the community's attention focus on the feedback. But as I mentioned before, I will talk more about forcing. In terms of the estimate of ECS, something we have to mention is Gregory method, which is the most widely used way to calculate ECS. However, it has been established that the Gregory method generally underestimates the true ECS by around like 15% compared to the more accurate long-run integrations. Taking a high ECS model, CESM2 as an example, the CESM2 was reported with ECS of 5.3K. However, as you can see here, from the time series of energy imbalance and surface air temperature anomaly, the surface temperature anomaly at year 1000 after quadrupling CO2 is around 12K, suggesting the true ECS from a doubling of CO2 is at least 6K and likely greater, since the model is still far from reaching the equilibrium at year 1000. Previous study usually attribute the ECS underestimate to tight dependence of climate feedbacks, owing to the time evolving surface warming pattern, nonlinear state dependence of radiative feedback. However, we may have different opinions on this. Here I'm showing a typical Gregory plot with energy imbalance versus the surface air temperature anomaly. The traditional Gregory method regulates the energy imbalance against the temperature anomaly using the first 150 years, with the slope provide an estimate of the climate feedback pyramid, and the y-intercept is providing an estimate of the EIF. The quotient is twice the ECS, as we are using the quadrupling CO2 simulation, as we already knew Gregory method underestimate the true ECS compared to the more accurate long-run integrations. Here, the true ECS is extrapolated by using the final 50% warming period of more than 1,000 years simulation for the following Rosenstiel et al. Method. If we add the most accurate radiative forcing diagonals, which is the land warming corrected EIF from the fixed SSD simulation, we would find the Gregory method not only underestimate the ECS but also underestimate the EIF. So if we connect the most accurate EIF and ECS results, we could have a new line for the equilibrium feedback according to the definition of Rosenstiel and Carl Armour's work. We will find the slope of Gregory method agrees very well with the best estimate of the equilibrium feedback parameter. This is true in all models for which both fixed SST EIF and long-run coupled quadrupling CO2 simulation are available, and suggests it's a bias in EIF, not the feedback, that causes the low bias in the climate sensitivity from Gregory method. Is there a way we could fix the underestimate ECS, as there are only 4 mixed model with the long run for true ECS calculation, and only like 17 models with the provide fixed SSD simulation. We cannot rely on the true ECS or true EIF simulation to accurately diagnose ECS for all models. Hence, we need another method. Since the climate feedback pyramid becomes less negative as the climate approach to equilibrium, we can expect more accurate EIF estimation from the regression on the shorter period. For example, like the conventional record length first 20 years. It turns out the first 20-year regression provides a much more accurate EIF estimate than the original Gregory method. Here, comparison between the coupled EIF estimates and the land warming corrected EIF are shown compared to the uniform 50% underestimation of the EIF by the Gregory method in the blue diamonds. The first 20-year regression showing the red circles provide EIF estimation much closer to to the EIF elasticity. In this case, we propose a modified method to estimate the true ECS in a standard 150-year simulation using the EIF from the first 20 years and the feedback from the whole 150 years, just like the equation shown here. Compared to the underestimated ECS by original Gregory method shown in the blue diamond, the modified method replicates the true ECS diagonals from the long-run coupled simulation. The bias in ECS is reduced with the modified method close to the highest accuracy we can acquire from 400-year-long coupled simulation. With both the Gregory method and our modified method, we revisit the effective and equilibrium climate sensitivity for both simplified and semi-cis ensemble and see the difference between effective and equilibrium climate sensitivity for full model ensembles. Our results show the equilibrium climate sensitivity is around like 12% higher than the median, higher than the effective climate sensitivity. The value is less than the 17% in Shiru et al. Assessment. So for this work, we show it's the bias in the EIF instead of the feedback that cause the low bias in the ECS from the Gregory method, and our modified method replicates the best ECS estimate from the thousands year run coupled simulation, providing an easy and effective way to diagnose the true ECS. And the estimated ECS from quadrupling CO2 simulation is like 12% higher than the effective climate sensitivity. As we already know the importance of accurate estimate radiative forcing for climate sensitivity diagnosis, it's important to better understand the cause of intermodal square in radiative forcing and its implication for climate sensitivity in the following two parts. The radiative forcing we saw before is the total radiative forcing or effective radiative forcing, which includes the instantaneous radiative forcing from the forcing agent perturbation, and the rapid adjustment occurred without any surface temperature change. Here, the most important one is the stratosphere temperature adjustment. So if you add CO2 into the atmosphere, the stratosphere would cooling and add 1 watt, probably 1 watt per meter square forcing into the system. This work we would focus on the IIF since instantaneous radiative forcing or IIF, since the IIF is the best understood aspect of the radiative forcing. However, the IIF has the huge intermodal square, as you can see here. The IIF from a doubling or quadrupling CO2 concentration varies by like 50% among climate models. Although this square has persisted for nearly 3 decades, its underlying cause has never been fully resolved. Here I will briefly introduce the double call calculation which we use in this work. It's the most accurate way to calculate the IIF. For the calculation, we will fit the base state conditions such as the surface albedo, temperature profile, humidity profile, clouds into the radiation codes. For the first call, so we can get the flux at like TOA, and for the second call, we fit the same base state, except with the perturbed forcing agent, like such as doubling or quadrupling CO2 concentration. The flux difference between the second call and the first call is the IIF. Even though CO2 is well missed greenhouse gas and uniformly distributed. But as you can see here, the CO2 IIF has an inhomogeneous distribution. This inhomogeneous distribution is due to a dependence on the climatological base state. Recently, Zhuangji et al. Clarified the state dependence of CO2 IIF with an analytical model. According to their model, CO2 forcing can be considered as a swap of surface emission for the stratosphere emission. In other words, the higher surface temperature means the higher IIF. While the higher stratosphere temperature means lower IIF. This highlights the importance of the surface temperature and the stratosphere temperature to the CO2 IIF. Here we would like to see if the state dependence of CO2 IIF help to explain the stubborn intermodal spread in IIF. Here we first show the unlike double core result available from the SIMIFICE and SIMICIS model for the historical ellipse experiment. Again, the results show the stubborn spread consistent with previous estimations. To better understand how much of the spread is resulted from the base state difference, we conduct a comparison between the online and the offline double core IIF here. Note the online double core results have both radiation code difference and the base state difference. But for the offline one, we use the same radiation codes for all models, so it only has the base state difference. If we ignoring the outlier, as it shows an increase with high within the stratosphere, we can get a correlation of like 0.8 between the online and the offline calculations. This means most of the intermodal difference in the IIF is due to the difference in base state, not difference in the radiation codes, and suggests that the climatological base state play an important role in determining CO2 IIF. And we found most of the intermodal spread in IIF is due to the difference in the stratosphere temperature. Based on the scatter plot between the stratosphere temperature versus the offline double core IIF. The influence of the base state on CO2 IIF is more clearly illustrated in the online double core results with the 1% CO2 base state. As you can see here, the result reveal a dramatic growth in the IIF as the climatological base state evolves. For both models, the IIF increased from like 5 watt per meter square when the IIF is computed in a pre-industrial climate to around 8 watt per meter square when it's computed in a higher CO2 climate. This challenges the widely held assumption the IIF from a doubling or quadrupling CO2 is constant. To the contrary, it demonstrates that the CO2 IIF is a dynamical quantities that change as the climate changes. And we find the IIF from doubling CO2 increase by 25% for each doubling of the base state CO2 concentration. So these results consistent with the analytical model we mentioned before. The higher surface temperature, the higher IIF, while the lower stratosphere temperature, also the higher IIF. To assess the relative contribution of these change in climate to the IIF change, to the IIF increase, we include the unlike double cost results with the quadrupling CO2 base state. Despite having a similar surface temperature change, the IIF in the 1% CO2 experiment show a much larger increase over time. This means a strong dependence on the stratosphere temperature. So the stratosphere cooling from the CO2 not only add an additional adjustment of like 1 watt per meter square to the IIF, but also it also make the subsequent change in CO2 more potent with no punch between the IIF and the stratosphere adjustments. This dependence will tend to make the high CO2 climate more sensitive than low CO2 climate. And the climate sensitivity increased by like 60% for each doubling of CO2. So based on our results, we know the CO2 IIF is not a constant, it's a dynamic quantity that changes as the climate changes. Additionally, the IIF for doubling CO2 is about 10% larger today than it was in the pre-industrial era period due to the change in the base day primarily from the stratosphere cooling. So with this work, we now know the CO2 radiative forcing better, but can this work help us to know the past or the future Earth better? I guess the answer is yes, since the stratosphere temperature plays a dominant role in determining the CO2 forcing and also greenhouse effect. We can get a conclusion. Any change in the atmospheric agents that perturb the stratosphere temperature could subsequently impact the climate. Taking the recent polar ozone depletion as an example, the ozone depletion has lead to a strong cooling within the stratosphere and further amplification of the CO2 forcing. As our results suggest, it should contribute to local warming, right? Here we quantify the surface warming effect from the ozone depletion will amplify the CO2 forcing as a nonlinear warming contribution or the covariance of CO2 change and ozone depletion, which is the difference between the historical temperature change using all forcings and the sum of different components like greenhouse gas only, aerosol only, natural variability only, ozone only. As we expected, the most of the indirect surface warming occurs around poles, where the upstratosphere temperature show the strongest cooling. This supports the idea we had before. Any forcing agents which perturb the stratosphere temperature could also impact the climate by modulating the CO2 IIF without change CO2 amount. It may have important implication for understanding the cause and the consequence of decline paleoclimate. Also, our results also have the implication for the geoengineering and the climate mitigations. Taking the year 1992, which following the eruption of the Mount of Pinatubo as an example, the inject volcano aerosol within the stratosphere not only cool the surface by reflecting more solar radiation back to space, but also warm the stratosphere by increasing the atmospheric absorption of the sunlight in the stratosphere. The resulting stratosphere warming also weakened the CO2 IIF and mitigate the warming efficacy of CO2. This provides a new perspective from the long-way side to consider the geoengineering instead of solar radiation reflection only. So different from the common solar radiation management by sulfate aerosol injection, we have a new idea on the geoengineering by adding black carbon to the upper stratosphere to warm the upper stratosphere and weaken the CO2 greenhouse gas effect. So we can see, so in this case, we can see like more OLR in the FTOA and less net radiative flux into the Earth system. To summarize this part, more than half of the intermodal spread in CO2 IIF could be attributed to the difference in the base day. The IIF for given CO2 perturbation is not constant, but strongly depends on the base day. The IIF from a doubling CO2 increase by 25% for every doubling and has increased by 10% since pre-industrial period. It may have important implication for the deep paleoclimates and also for the geoengineering. Continuing the IIF work, we conduct a comprehensive investigation of the evolution in the simulated radiative forcing and try to see if there is any progress in the simulated radiative forcing for the recent 2 decades. Before I introduce the more accessible method for calculating the radiative forcing, it's important to introduce the forcing feedback framework. Given a forcing agent perturbation, we will first see the instantaneous radiative forcing, then the rapid adjustments without any surface temperature change, and the radiative response following surface temperature change. Here, the radiative kernel method can be used to diagnose the sum of adjustments and feedback. The residual between the TOA flux anomaly and the sum of the adjustment and the feedback is the IIF. As we mentioned before, the IIF measures the change in the net radiative flux from the change in forcing agents from like greenhouse gas, aerosol, natural events. To see the improvement in the recent CMIP, here we first compare the IIF at year 1992 following the Mount Pinatubo eruption. The results show less model have the positive radiative forcing in the year from CMIP 3 to CMIP 5 to CMIP 6, meaning improvement in using more realistic forcing input. And compared to the CMIP 5 results, CMIP 6 show less negative radiative forcing in the 1992, indicate less negative aerosol forcing or weaker aerosol radiation interaction in the most recent generation of climate models. It also shows in the aerosol-only simulation from CMIP 5 to CMIP 6, suggesting the less negative aerosol IIF in the CMIP 6 compared to the CMIP 5 could be the cause for the less negative aerosol EIF in the CMIP 6, as you can see here. However, for the last year of the CMIP 3 historical simulation, or the year 1999, we cannot see noticeable difference among the recent 3 CMIPs for either either the modal square or the forcing magnitude seems like have value input in a simulated greenhouse gas radiative forcing. However, we will see some difference in later. And we also compare the radiative forcing obtained from coupled and fixed SST simulation, since there is a widely held assumption the radiative forcing obtained from the fixed SST simulation is more accurate than the forcing obtained from the coupled simulation, with less uncertainty related to feedback process. However, our results show the IRF calculate from from coupled simulation in a relay and the fixed SST from the black line matches very well. Since the coupled simulation is more like close to the real climate or real world, and the fixed SST is the most accurate one. This means the possibility for a more accurate killing curve could be made by using satellite observation. Meanwhile, we also check the cost for the EIF uncertainty from both fixed SST and the coupled simulation. The results show the cloud adjustment and IRF have the strong correlation with the EIF, are the main source of the EIF uncertainty. Since EIF shows increase in the CIMIC 6, we also check the cost for it. Feel like the stronger, we can see the orange bar, feel like the stronger stratosphere adjustment is the cause for the higher EIF. But if we consider the vertical resolution of CIMIC 5 and CIMIC 6 outputs, the two more layers in the CIMIC 6 output lead to the stratosphere adjustment difference. If we correct it, we can see the difference is due to the IIF difference. Due to the final resolution and colder upstratosphere temperature. So the IIF increase is the cause for the EIF increase in the CIMIC 6. So our results show little progress in the radiation scheme in the recent 2 decades. The radiative forcing estimate from coupled simulation is well matched with that estimate from the fixed SST simulation, and IIF and the cloud adjustment determine the uncertainty in the total EIF. And the higher EIF resulted from final vertical resolution lead to the higher EIF in CIMIC 6, contributing to the higher ECS. So I will just start here. Thank you very much for your attention. I'm happy to take questions now.
Jason, where will you go?
Thank you so much for your talk. Any questions? Yes.
Okay, well, let's just go back to that previous slide. Next one. Oh, no, forward.
This
The
one.
next to last slide.
The words.
Yeah. There, okay.
This one.
What do you mean by little progress in radiation schemes in the recent 2 decades?
So we think almost no progress or no improvement in the CIMIC.
What is your metric for that? The fact they don't agree with each other? Is that
So because we don't see the change, like not only in the magnitude, also the intermodal spread is still there without any change for like 3 decades.
okay? So the models are disagreeing with each other still.
Yeah.
But you can't say that
Yeah.
none of those schemes are better than they were 20, or not better, whatever, you know what I mean, than 20 years
Yeah.
ago. Okay. So you're just saying little progress in convergence
Yeah.
of radiation schemes.
Yeah. I will change.
Okay. Don't change it now.
Yeah. I just took some notes.
Any more questions from our? Yes.
Haozhe, it's a ton of work, an amazing amount of work. I want to go back to, I have a question about a much earlier slide. I just want to make sure I understand. The long-term long wave feedback.
The first one, right?
No, way back, way back. A map, no, go back. It's a map of the long wave,
This one?
nope, keep going.
Okay,
Keep going,
I
keep
guess
going,
I'm-
way back.
The first one.
Part one.
Part one. That one.
Which one?
Yeah, this one.
Yeah.
Okay, so this is a picture of the mean feedback average over all models, or is it
No,
the
just-
spread?
So for this one, we do the regression.
Yeah.
So every model have their own local feedback.
Right.
So we using the regression of the local feedback of all models against their own global mean
Right.
feedback to see which region contribute most to the global mean spread.
And this is a picture of the average overall models, or is it the spread across models?
So this one just the contribution. You can think the higher value means the region have larger difference
Okay.
across models.
So this is a contribution to the spread of models from these feedbacks. No. All right, explain this plot to me because I want to make sure I understand it.
So for this one,
Yeah.
so you want to more like for the method part or for the result part?
I just want to understand if this shows the spread or the total or the average across models.
So this one is because for different models, for model ensemble, they have large spread in the
Right.
global mean.
Right.
So we want to know which region
Yeah.
have largest difference and
Right.
contribute the global mean spread.
Okay.
So the larger value here means there are large contribution to the global mean.
Okay. So like looking at this map, I understand the left one is probably an ENSO thing, right? So model simulation of ENSO is contributing to this spread and feedback. What's your interpretation of the one on the right? Why is it such a strong hemispheric asymmetry there?
Yeah, I think this could be due to like model. For some model, they have strong. It depends on like the Southern Ocean warming. Some model have strong one. Some model with weak one.
Right.
So it means we can even consider this
Yeah.
with the ITCG shift.
Okay.
So some model have stronger ITCG shift,
Yeah.
but some model have less, and finally lead to a symmetric things.
So you're saying that model differences in their simulation of the response of the ITCZ to forcings produce a spread in global mean surface temperature.
So I would say it's more like
Okay.
surface temperature lead to the ITCG difference and lead to this kind.
It leads to this, which then is how you interpret the spread in global mean temperature.
Actually, we also check the surface temperature. I didn't show here.
Okay. All right.
So it's more like, so we are just mention something like the Southern Ocean
Yeah.
warming difference is important for this one.
Right. I guess I wonder if there's anything. So you're saying this is reflective of where the ITCZ is.
Yeah.
I guess I'm wondering, are there other things besides Southern Ocean warming? No, I mean that's just one way of moving the ITCZ. What else is there?
Not sure.
Or that's the only one that you guys have thought about? Because you could get changes in ocean circulation that might move the ITCZ, or
Yeah.
changes in, the northern hemisphere, sea ice or something.
I guess I don't have the ocean
Yeah.
background, so
No, but it's alright.
the only
It's
thing
all-
I consider just from the surface temperature pattern.
Okay, good. Thank you.
Thank you, Amy.
Let's see if I can connect it. We have taken two questions.
From
We have taken 2 questions from in-person audience. Is there any question from Zoom?
No.
Any more questions for audience in the room? Still have around 5 more minutes.
I thought the talk will take much longer than this.
Yes.
Oh, that's fun. Do you have the time series of the IRF at the very end?
The last part.
Yeah. Yeah, that or any of them.
Okay, so this one.
Yeah, that's good. I was just wondering. I know the 91 blip you said was mounted in Tubo,
Yeah.
but so are the other dips just other volcanic
I
events
think
in the past?
this one also a major one.
Okay.
It's Krakatoa, right?
Yeah.
Okay.
And I guess this likely is just smaller, but the Pinatubo and this one are huge one.
Okay. So that's like the only natural thing that you're seeing that would change the stratosphere temperature and the IRF.
Yeah,
I guess.
that's the thing.
Okay.
Will strongly
I see.
manipulate the stratosphere temperature.
I see.
Any more questions? Very good. Thank you all for attending the last seminar of the year and the semester. Hope you all have a great Christmas break and Merry Christmas and Happy New Year.
Thank you, everyone.